multiplying and dividing rational expressions. How we accomplish the multiplication and division is the same way that we would handle a product or quotient between two fractions. So let's say I have a fraction 2/3 and I want to multiply it by 4/5. We know to do this, we just multiply the numerators and multiply the denominators to get 8/15. And at the end, we would look to simplify that. Or maybe before we multiply, we could also look to simplify each individual piece. Let's say that instead of 2/3, we had 8/12 times 4/5. What we could do is reduce this first to the 2/3 that we originally had, or you can perform the multiplication and get 32 over 60 and simplify at the end, dividing both by 4, we still get 8/15. So multiplication with rational expressions, because they're formatted as a ratio between two functions, will be performed the same way that we do multiplication with just normal fractions with numeric numerators and denominators. And with division, we know that division is the same thing as multiplying by reciprocals. So every division problem with rational expressions just turns into a multiplication problem. So dividing by 4/5 is the same thing as multiplying by 5/4. So understanding what division actually represents in its relation to multiplication will reformat our problem into something familiar when we get a handle on multiplication. So division is really no different except one additional step at the beginning. So let's look at some examples. Here we have rational expression times rational expression. What we can do is one of two things. You can perform the multiplication across the top and bottom right from the start, as we said before, or we can simplify within each expression and then multiply at the end. Simplifying within each expression first is going to give you some smaller numbers to deal with, as well as some smaller exponents or less variables to work with. So it's really a preference thing, but what we can do is both ways. I'll show both ways. So let's say we multiply across the top and across the bottom first. Here, we are going to get 3x, now multiplying variables of the same like term. We just add the exponents, so we'll get x third, y to the sixth, and then on the bottom we would get 24, x to the fifth, y. And then from here we can simplify. We just had a whole video on simplification. Now I'm down to one rational expression. So to simplify this, we look at the numbers. They're both divisible by 3, so that 3 becomes a 1, and the 24 becomes an 8. There's 3 x's up top, 5 on the bottom, so if I remove 3 from both, there's none left on the top, and there's 2 left on the bottom. For the y's, there's 6 up top, 1 on the bottom, for a total of 5 left on top when I remove 1 from each. And here is my fully simplified product of these two rational expressions. Now we should get that same answer if I simplify each one first and then multiply. So on this first one to the left, we could have canceled out the y's. I could have removed 1x from the bottom and from the top, and we could have simplified that first expression down to just x to the fourth. Then on the other one, we can simplify that 3 and that 6 to 1 over 2, and then x removed from the top, and we have x to the third on the bottom, and we still have y to the fifth over here. Now, if you want, you can also cancel diagonally. So I could remove that x from the top left and an x from the bottom right. But if we don't recognize that, we can perform the multiplication and get to this point. And then we simplify from here. We'll see we can remove a 1x from the top and 1 from the bottom to get a final result that matches. Oh, sorry, we should have had a 2 here from the 3 over 6. And that gets us that 8. X squared, which is exactly what we had before. I would recommend simplifying within the expressions first before multiplying, and again, you'll see why as we get to more complicated examples. But when we just have monomial terms in the numerators and denominators, so strictly monomials, it is not too bad of an option to just multiply across the top, multiply across the bottom, and then simplify. But in the event that we have polynomial expressions in our numerators and denominators, we don't necessarily want to do that because multiplying these out requires in this case, a triple distribution, and you can see why that could get really complicated really quickly, especially when ultimately our goal is to simplify. You're going to be dealing with a fourth degree polynomial that you have to factor down if possible. So my recommendation, when we have polynomial expressions, let's look to cancel before multiplication. And then we'll summarize the approach at the end of the video. But to identify cancellations, if you recall, through simplification, we should be factoring where we can. So the top left, we're going to factor that expression. We're going to have x minus 4, x minus 2. On the bottom, we have a quadratic where the a value is greater than 1. So we could do this split the middle, or you could recognize that you have perfect square minus perfect square, which is a special case scenario. It's a difference between two squares. So square root of the first term is 3x, 3x. Square root of the second term is 4, 4, plus minus. There's our factorization. The top right, actually let's do the bottom right first. There's another difference of squares, or the shortcut, a value equal to 1, what multiplies to negative 16, adds to 0, x plus 4, x minus 4, or you could use that difference of squares approach as we did in the bottom left. Now the top right, quadratic with a value greater than 1. We're going to have to split the middle there. 3 times 8 is 24. What multiplies 24 adds to 10, 6, and 4. So we're going to get 3x squared plus 6x plus 4x through the split the middle. Now we have a grouping problem. We're going to take out a 3x from the first group. And we're going to take out a 4 from the second group. So that now the two terms share an x plus 2, which we will factor out. And what's left over is 3x plus 4. So there's our factorization. Now that we've identified the factorizations of all numerators and denominators, we are ready to make cancellations. So cancellations, we need something present in the numerator and the denominator, and we can cancel diagonally too, because ultimately we're multiplying across. So that is a valid approach in this type of problem. You can cancel diagonally with multiplication. So we have an x minus 4, x minus 4. We have a 3x plus 4, a 3x plus 4. Nothing else cancels. So when we combine, now we can multiply across the top. We have x minus 2 times x plus 2 over 3x minus 4, x plus 4. And we can leave our answer like this. If you want to double distribute to get just a single polynomial up top, if that's what the directions want you to do, that's fine, but we can leave it as a product of binomials for now, just to illustrate how to multiply with polynomial expressions in the numerators and denominators. So your initial approach should be factor. That way we can identify cancellations, because identifying cancellations reduces the complexity of the problem and makes an easier multiplication at the end. Because if we did ultimately have to FOIL this out or double distribute, much easier than doing that triple distribution as we see there. So we could have x squared would be minus 2x plus 2x would cancel minus 4 on the top, and on the bottom we'll get 3x squared. 12x minus 4x is 8x minus 16. So if we did want to reformat as polynomial over polynomial, we could get this as well. Now let's jump over to a division problem with polynomials. Division, as we mentioned before, is the same thing as multiplication. So what we're going to do is reformat this problem, that instead of dividing by this second expression, we're going to change it to multiplying by the reciprocal of that. So we will first, this is our first move in division problems when we're trying to perform operations on these rational expressions. So we're going to change this to multiplying by 2x plus 1 over x squared plus 4x. Now how we handle the multiplication problem is the exact same as before. To avoid a complex distribution, which is a triple distribution, we're going to factor and cancel to reduce the complexity. So up in the top left, we have to do the split the middle. 4 times 9 is 36. What multiplies to 36 adds to 15. That should be 12 and 3. So we'll get 4x squared plus 12x plus 3x plus 9. So then grouping problem, we take out a 4x, x plus 3. Take out a 3. Now both terms share the x plus 3. Remove that. What's left over? 4x plus 3. So there's our factorization of the top left. bottom left. Split the middle because we have an a value greater than 1. 8 times 3 is 24. What multiplies to 24 adds to 10. That is 6 and 4. Remember the split, the order of the split doesn't matter. If you did the 4 and before the 6, it should still work out. Take out a GCF. What do I have to remove from the second group? A positive 1. That's already what I want. 4x plus 3, 2x plus 1. Then we have times. I can't do anything with the top right. That's a linear equation, so there's no factorization to be had. There's no GCF to pull out. On the bottom right, we have a quadratic, but when there's no C term, so when the C term is not present, I can't do a factorization into two binomials, but rather my factorization is going to require a GCF. In this case, we can remove an x. So when you see no C term in the quadratic, that's indicative that a GCF needs to be removed and not creating a product of two binomials. So be careful there, and we're left with x plus 4. Now let's look to see what we can cancel out. Remember, with multiplication problems, we can cancel diagonally because ultimately we're just multiplying across the top and the bottom. So we're going to combine it into one rational expression at the end anyway. So the diagonal relationships will end up just being right over each other vertically at the end. So that is allowed. We can cancel out a 4x plus 3 that's present in the top and bottom. 2x plus 1, 2x plus 1. Nothing else cancels. So what's left over? We have x plus 3 on top, and we have x times x plus 4 on the bottom. If we want to reformat this so it's not a product of terms, but rather just a single polynomial expression on the top and the bottom, we can have this. So there is a rational expression that is the most simplified version of the original division problem. Okay? So when dividing these two rational expressions, this is the simplified result. So division is just multiplication in disguise, and that is what you're going to do when you see a division problem reformat. So let's condense down the steps for multiplication / division. We'll make a start. This is a first step if it's division. So if division, rewrite as multiplication. Which again is division equals multiply by reciprocals. Okay, so dividing by a is equal to multiplying by 1 over a. Okay, that's what we're saying there. So that's the first thing you want to do if you have a division problem. If you have multiplication, then we're ready to go. First thing, factor all numerators, denominators, if possible. So in the event that your expression is just a monomial term, there's only a single term in there, you're not going to be able to factor it. Or if it's linear, you might not even have a GCF available. So there's always a possibility that it's not factorable, but if it is, you want to do that. Then, once you have everything factored, make cancellations. Remember, diagonal cancellations are allowed in a multiplication problem. We can't make horizontal cancellations. Once we've made all the cancellations, then we're going to multiply across the numerators, then across denominators. And once we have done that, just double check that your final result cannot be simplified further. And there's the whole process for multiplication and division of rational expressions with some examples included.